So we say that a permutation contains a shorter permutation as a pattern if there are entries in the big one which relate to each other the same way as the entries of the short one. So in this case, the big one, 5, 7, 8, 2, 1, 3, 4, 6 contains 1, 3, 2, because if you look at the 3 red entries, they behave like 1, 3, 2. The first one is the smallest, the second one is the largest, and the third one is the middle one in size. Is this clear? Like you have absolutely no doubt whatsoever at all. Okay. Well, it's a well-known definition, but still not everybody knows it. These are famously hard to enumerate. I will not spend time on explaining how hard, but very hard. Okay, so now let's look at the ordinary generating function for the number of permutations f and q, avoiding the given pattern q and of length n. So I have a theorem from 2019 which shows that in a very strong sense, for most patterns, this generating function is not rational. And this is what I mean by most. I can prove that the generating function is not rational if the first entry of the pattern is not 1, or the last entry of the pattern is not the maximal one, or neither of those is true, but the pattern is equivalent in the sense that the number of permutations avoiding it is the same as the number of permutations avoiding another pattern, which satisfies 1 or 2. So if one of these 3 holds, then I can prove that this is not the generating function is not rational. In the other cases, I always believe that the generating function is also not rational, but I cannot prove it, except for the trivial patterns 1, 1, 2, and 2, 1, because for those it is rational and trivial. So unfortunately, 2019 was 6 years ago, and since then, there was no progress. So that in the remaining cases, just a totally different method is needed, because the trick that works for the others doesn't work in this case. Okay, and also if you want to avoid more than 1 patterns, then nothing like this is true, because there are these very simple counting sequences that have rational generating functions. But that's a different problem again, because if you want to avoid more than 1 pattern, then it's a much more restrictive condition. Okay, so now let's turn to non-algebraicity, right? It's much harder to prove that something is not algebraic than that it is not rational. And in fact, until 2021 or so, the only technique I knew that applied in pattern avoidance was a classic result of Jungian, which was based on this, that if the generating function's coefficients asymptotically are like that, so constant to the n over n to the m, where m is a positive integer, then the generating function cannot be algebraic. So you have to know the asymptotics at a high precision, and typically you don't. For pattern avoidance, you usually don't. The only time then we did know that was if the pattern was monotone and of even length. Well, for a monotone pattern, this inequality holds. Let's see if I can use the pointer. Yes. Yeah, so this asymptotic equality holds. So if you look at the denominator for even n, this will be an integer, hence Jungian's theorem will apply. So the generating function then is not rational. But that was the only case, the monotone case, when we could say anything, and then only if k was even. And so in 2021, I had an idea that a certain strengthening of this could work, but I also knew that I couldn't prove it. And then I asked who could possibly prove it, and the answer I got was that probably Alin Bostan could. It's too bad he's not here, because I basically asked him to prove the theorem, and he did. So I basically ordered the theorem, and I got it. And here it is from 2021. Alin, I'm sorry, there should be an E at the end of his first name. So take again a power series, and now we weaken the condition on the coefficients. So the coefficients have to be between two constant multiples of what it was in Jungen's theorem. So in Jungen's theorem, they had to be asymptotically equal to that, but now it could be two different constant multiples. Okay, and so it's a little bit like the squeeze theorem from calculus, that you have a sequence and you squeeze it between two other sequences. And even then, if this proves, then Fz cannot be an algebraic power series. So we can reach the same conclusion from less. And I have a textbook application for this. That's why I needed the theorem, because I knew how I could prove my result if I had a theorem like this. So now I have it. So consider permutations that avoid those four patterns. Sorry, these four patterns. So in other words, if you have an increasing subsequence of length 4, then after that you have to keep going up. Okay, so you can't come down anywhere after you had an increasing subsequence of length 4. And yeah, here is a picture like this. At the beginning, you can do anything. At the beginning, your permutation can do many things, but once you reach an increasing subsequence of length 4, you have to keep going up. And this suggests a natural decomposition of permutations like this into two parts, namely the first part when you can do anything, and the second part when you can do nothing but go up. But this picture also shows what the problem is with this, is that you don't exactly know where the cut is. Because when I say at the first part, you can do anything, that includes that you can end with an increase. Right, because the first part is until you reach the increasing subsequences of length 4, but you will reach that with an increase, or with an increasing subsequence of length 2 or 3. But the point is that you can't have an increasing subsequence of length more than 4 there, right? Because then you are already at the second part. So they say every talk should have a proof. So here, this is my proof, that if you have a permutation which avoids those 4 patterns, then you can decompose that permutation into two parts, where the first part avoids 1, 2, 3, 4, and the second part is increasing. And the decomposition is not unique, but there are at most 4 ways to decompose every permutation like this, because of what I said, that the first part can end with an increase, but it can end only with an increasing subsequence of length no more than 4. And that's precisely what we need for the theorem, right? That with this, I provide a lower bound and an upper bound. The difference between the two is a factor of 4. So I squeeze my sequence between two sequences which are a constant away, right? And that's exactly where Bostan's theorem applies, right? That therefore, if I can prove that these are of the right form, then I'm done. Then the generating function of this sequence is not algebraic. Okay, and I can do that because Fi is the number of permutations avoiding 1, 2, 3, 4, and that's, we know from the Regev's theorem that those are roughly 9 to the n over n to the 4. And this thing that I do with them, that is called a binomial transform, and it's not hard to prove with elementary methods that then the binomial coefficient turns 9 to the n into 10 to the n. And so this holds, and therefore by the Bostan's theorem, the one that looks like the squeeze theorem, the generating function of the sequence in the middle is not algebraic. Okay, so yeah, this was what never mind. Yeah, so these are other questions, other problems. Sorry, so let me go back. So, never mind distinguishing two cases. Let's look at other conjectures we had in the field. So what are these things? What do these things mean? I haven't defined them. So the pattern class that we looked at, the pattern avoidance problem we looked at, was that if you go up 1, 2, 3, 4 after an increasing subsequence of length 4, you can have only even bigger guys, like 5. Now this said, the first one here says that if you have an increasing subsequence of length, of length 4, then after that everything has to be at the second level. And the next one says, that everything has to be at the third level or everything has to be at the fourth level. So numerical evidence for each of those three problems suggests something like that, that the numbers of those permutations avoiding those sets of patterns are 9 to the n over n to the 3, which would again mean that they are not algebraic. The generating function is not algebraic. Interestingly, that for the last class, which is not here, namely where it's A51. So after you have an increasing subsequence of length 4, you have to go all the way down to 1. So for that, we can't even prove the exponential upper bound of 9. We think it's true. We also think that more precisely, the asymptotics are 9 to the n over n to the 4, but we can't prove even the exponential upper bound, which is interesting. Why is that problem more difficult than all the others? I mean, again, the method that worked in the previous cases doesn't work there. Okay, so you could generalize this to longer patterns, which we did, but the ideas are not that different, or patterns in which it's not all increasing, but the first two are decreasing. But again, the ideas are not too different. Now, yeah, these are other similar generalizations. Now, let me show something else. Here is another thing. While we've looked for other examples of applying this method, we logged into nice identities or seeming identities that, that our problems were probably equivalent to other enumeration problems that people found in other fields, which were also difficult and they couldn't solve them. So here is one. So it seems, and I would have never found this if I hadn't considered these non-algebraic results, that these two pattern avoidance classes are the same. Now you would say, who cares? It's just three random patterns of length 5, but no. So if you look at the right, that has a lot to do with stack sorting, if you heard about stack sorting of permutations. So there is a family of 64 problems. 64 is 2 to the 6th. That's not an accident. So 64 problems, out of which 63 are solved. And the one that is not solved because nobody can enumerate these permutations. Okay, so and so that's a problem which is more difficult than any other problem in its family. And it happens, I mean, for the first 650 values of n, it's the same as our sequence. So it could be that they are difficult for the same reason. And in particular, the generating functions are probably not algebraic. Okay, so while looking for examples to apply our method to prove non-algebraicity, we stumbled upon other problems which might be difficult for the same reason. And otherwise, we would have never stumbled upon this. Okay, another example of using this method was when with Alex Borstein, we counted permutations that contained exactly one copy of a given pattern. So not 0, but exactly 1. And here we proved this chain of inequalities. So in the middle, that Sn dot monotone 1, that's the number of permutations that contain exactly one copy of the decreasing pattern of length k. And we were able to squeeze it in between these two numbers, which both are about the monotone patterns. And one of the inequalities here is trivial, the first one, but the second one took a nice injection. And so remember what I said 10 minutes ago about the monotone pattern, that if it's of even length, then it's the right growth rate. So the generating function is not algebraic. So here, because I was able to squeeze this in between two constant multiples, because this is just k squared times, they only differ by a factor of the power of k. Therefore, again, Borstein's theorem applies, and the generating function of the sequence in the middle is not algebraic. Okay, and so yes, finally, pattern avoidance is not the only way, not the only field where this can be applied, because there is also these different kind of objects, finite words over a finite alphabet. We say that a word has a border if u is a non-empty prefix and suffix of w. Okay, so for instance here, this word has border 0, 1 because 0, 1 is both a prefix and a suffix. And yeah, a word is closed if either it's at most of length 1 or it has a border that occurs exactly twice. So at the start, at the end, because it has to be there, but it can't occur anywhere else. So for instance, entanglement is a closed word because ent, right? Beginning and the end, but nowhere else. But eerie is not closed because the E is the border and it occurs 3 times. And Daniel Gavric proved that the closed words, the number of closed words satisfies this chain of inequalities. Hence, by Boston's theorem, again, their generating function is not algebraic. Okay, and I'm done, but because I still have 2 minutes, thanks to starting early, I would say that there's a version of this privileged words where a word is called privileged if it's either of length at most 1 or it's closed by a privileged word. So at the beginning and at the end, the border is a privileged word. My favorite example is alfalfa, right? Because alpha is both a prefix and a suffix, and it occurs exactly twice. And alpha itself is privileged because it starts with A and ends with A. Okay, so alfalfa is privileged. And so in that one, the bounds are different because it's not just constant to the n over n, but this time over n times some factorials. So that's the next thing to do, to prove a version of Boston's theorem where you can also have some logarithms at the denominator, not just n, but n times log n or something like that, n times log n, things like that. And I give the word back to you.
Question. Is there any hope to compute the transcendental generating function when you know that there is no algebraic one?
I don't think there is. So I will say one thing, that in the case of 1, 2, 3, 4, there's an exact formula known. So not for the generating function, but for the coefficients. So that may be more possible than get the transcendental generating function.